Please sit to the front. Today we're gonna do lectures on quantum spin, and this is the foundations or the basics of quantum information processing, or quantum computing, if you prefer. We first want to introduce some common single qubit gates, and then we will go to quantum discrete quantum tomography. I'll explain what that is later. So we know that what is quantum information? Quantum information is a highly interdisciplinary field. But what's the basic essence of it? Well, first we need to have quantum, right? Some quantum element in it, and that would be, for us, that would be superposition. Remember, when we talk about quantum, it's always, what's the quantum superpower? Superposition, and in some occasion, entanglement, and that's all. So that's the quantum superpower. And when you talk about entanglement, that concerns more than one qubit, right? So 2, 3, it needs to be more than one. Okay. How about information? I'm not a computer scientist, but when it comes to information, what can you think of? If you have a computer, right? What's the most important element in it? Or what's the most expensive? Is it the fan? GPU is a processor, right? So you need processor. What's the second most expensive element in it? Huh? Storage. So that's memory, right? So it's basically these two that cost a lot of money. When I buy a new laptop, they give me options on how fast I want this computer to be and how much storage I like in terms of hard disk, but also flash memory, right? Flash memory are for temporary storage, and they are part of the processor, information processing. They are used in the process of information processing. Okay, so these are the two most important element we need for quantum computation or quantum information processing. Okay, so let's talk about memory first, because this is simple. How do we store? So memory is to store informations as code, right? So if you, in my age, like when I was a young boy, we used floppy disk. Do you know what that is? So it looks like a square with a little tape, with a hole in the middle. That's the big one. The small one doesn't have one. But anyway, there is some kind of tape inside. Those tapes are magnetic, and you stored information. I think I would imagine it as like a collection, a bale of tiny magnets. And the way you store information is you flip this magnet up or down. That's how, you can correct me if I'm wrong, if I know better about this than me. But that's how we store information. We map information, say a picture, right? A picture is consists of pixels, right? We break information into the most basic element, and we try to represent this element for example, RGB code. Anybody know what that is? So if I have a picture, right? Each pixel has 3 numbers associated with it. How much red you have, how much green you have, how much blue you have. So this sort of is like an intensity scale from 0 to 255. So you give it a number like 169, 50, 13. That gives you a color, a specific color. And the picture has all its pixels coded with this RGB. So in terms of position and intensity in each color, right? So that's how we store information. We transform them to the most basic element, and we map that to a physical orientation of this tiny magnet in this case of the floppy disk. Okay? So that's all I know about computers. But in quantum information processing, we store information to quantum bits. And quantum bits consist of course, 0 state and 1 state, right? But what made it special is the ability to do superpositions. So through positions, each quantum bit, so 1 bit, 1 qubit, quantum bit is called qubit. 1 qubit has these 2 values. So through proposition, each qubit can represent almost infinite amount of possibilities. Remember this in this presentation? We talk about when we talk about Bloch sphere, we use this presentation, right? And the phi and the theta has their geometric meanings on the Bloch sphere, right? But this basically is a superposition, a general expression of superposition states between 0 and 1. And you can see, as you can see, that this can take any value, and this can take any value. So if, let me just say, if this, for example, what happened? Yeah, pi over 2. Oh, wait, should I have theta here, or did I have theta? Theta over 2. I forgot, because I'm supposed to have pi over 2 to put it. Okay, never mind. Do you remember? Oh, okay, let me just use this for now, for the sake of our argument. So this will represent a number. Oh, yeah. This is this. Okay, my memory is not screwed up. So this, correct? So this will represent a number, right? One number. And this combination can mean, I don't know, they can map to something like, for example, I'm just giving a random example. This can map to a color, okay? And so this is like R, a letter. This can map to a letter. And the other one, Okay. This can map to another letter, say L, right? So in classical bit, every bit, so one classical bit, there are two possibilities. And that's the most complexity you have in this bit. You can represent, use this to represent a letter. This is a letter. But for a quantum bit, you have so many different combinations. This list goes on and on and on, right? So you can use a quantum bit, even just a single quantum bit, to represent so many uh, things. The other thing is, so this is the power superposition. The other thing is entanglement. So entanglement. So if you have multiple bit, so say two quantum bit. If you have two quantum bit, then you will have four possibilities, right? And all their superpositions. Yeah. So for example, let me just. Okay. Okay. So now, if we design this to be the binary digit, so that this represent, so M M K. So if we let this to be 2K, and this is 20K. No. How does it work? Are you an expert of binary coding? So how do you represent 7? Huh? Yeah, how do you represent 7 in binary codes? 4 0 1 1 1 1 1 0 4 2 1 0. No, 0 1 1 1. Yeah, my bad. Okay, 0 1 1 1. Okay, so this is um, 1 for this. Gosh, is this 0 1? So is that how it work? So so this is to the power of 0 to the power of 1 to the power of 0 1 2. 2, right? Yeah, that's why it's 4. Okay. And then 2 and then 1. All right. Great. Okay, just in case you are like me, who is very ignorant of how to use binary to code numbers, this is how it works. So you have a string of numbers, 0 and 1, and the first digit is the power of 2. Is this 20? Oh, right. So the first digit represent 2 0, and if it is 1, that means you add 2 0 to your number. And if this is the second number, represent 2 to the power of 1, and if it is 1, you add 2 to the power of 1 to your number. And this is the third is to the second. So if this is 1, you add it to your number. So this will add to 7. Okay. How do you represent 3? 1, 0 on 1. Yeah, but we have like a 3-bit string. Great, good. So 5. 101, right? Yeah. Okay. So great. We are on the same page. All right. Um, so we could do this with a quantum bit, just like we did with the classical bit, right? We can assign each combination. Like for example, this will be, so in binary code, this will be how much? So this represent 2 to the 0 power, to this represent 2 to the first power, right? So this will be 1 plus 2, this will be 3. How much would this be? Okay, great. And this will be 1. This will be? Huh? 0. Great. So now we have 4 numbers. Yeah? So classical bit could do that. If we have a classical 2-bit string, we have 3 numbers at our disposal. But what's cool about quantum register, so we call this a register, this string, physically we call it a register. A quantum register could have superpositions, okay? And since this is a product state, the product state, the superposition of product state is entanglement. Okay, so this is super, that's why it needs more than 1 qubit, superposition of product states. Okay, so in this case, it's not like we are adding this number, but we could have this bit representing 0, 1, and 3 at the same time, okay? And if we can present this number, these 3 possibilities at the same time, we can process them at the same time. Okay, so that's all I can say, what I want to say about quantum memories, quantum registers. Okay, so register. Register is the physical realization of the memory, okay? How about processing? Processing is the ability to control the state of the bit, right? In the classical case, how do we change this to this? We probably apply a voltage and it will flip. It's direct, some kind of physical orientations, okay? Or we give it a charge. We can do something to change its physical state so that this goes from this transform to this, or this transform to that. Yeah. For qubit, we want to do the same thing, except here our test case is harder because now we have like infinite possibilities. I'm talking about 1 qubit. We have infinite possibilities, right? And if you want to just go to like an arbitrary state, how do you do that? If your state is initialized in 0, ground state, how do you go to an arbitrary state in a deterministic way? Yeah.
Can I just ask, so for one classic qubit, we have 2 different positions?
Yeah.
Which means
2 different configurations or orientation, yeah.
And in the classical sense, we can vary phi and theta?
No. The classical bit doesn't have this compatibility. For the that's for the quantum, right?
Yeah. So for the quantum, for 1 qubit, we could vary theta and phi from 1 to 5.
Right.
And thus we could get infinitely many configurations.
Yes.
Is that it?
Yes. So all the dots on the Bloch spheres can be represented by 1 single qubit. So that's how many letters you can access to, right? More than 26, I suppose, right? So So now the question is, how do we go from ground to an aperture configuration? How do we do that? Okay, let me state it again. So in the for classical information processing, we need to do like calculations with this register, right? We need to use them to combine and add them, divide them. Like we need to do computations with them. We need to switch this to that, switch this to that. We need to do that kind of fundamental transformation. Okay, because there are two possibilities, so the task is relatively simple. Now we have so many configurations for qubits. We have so many configurations, the infinite number of configurations. So the task is harder. So how do we go from 0 to this, or even from an aperture, any given initial conditions to another specific qubit orientation? Like for example, so how do we, well, for example, how do we go from here to here, right? So this is a superposition state. This is also a superposition state, right? How do we go from here to here? All right, so that's our topic, our first topic today. Single qubit gate. Gate means transformation. Or to be more specific, it's unitary transformation. Why is it called unitary? Reversible. That's a very important viewpoint. But it's not the most fundamental reason. Why is it called unitary? Anybody has been in a class of linear algebra? What?
The magnitude on the box sphere doesn't change.
Array. Yeah. So if this is the operator for the gate, and you operate on a qubit, right? And you transform it to another qubit, right? During this process, the magnitude of the qubit vectors on the Bloch sphere does not change. Yeah, okay? And that's actually an important requirement. So what that means is in a sense, what that means is the total probability remain the same after transformation. Like that's the most fundamental meaning of it, unitary transformation. It does not change the total probability of your quantum state. So whatever you do to it, the probability of finding your qubit in one of the configuration is still one. Like if you add all the probability of all the superposed states, okay? So the total probability remains one. This seems to be a very basic physical requirement, right? But not all operations can have these conditions. Okay. All right. So if you would like to have total probability remain one, you need to have this. Okay, that's a necessary condition. You need to have this. Okay, and that's why, and of course, this is the same as this. So that means that the reversed transformation the reverse transformation is its Hermitian conjugate. And this means you can reverse your calculation from your output to get back to your input. And that's actually a very special property of the reversible computation, or the reversible transformation is actually a very special property of quantum information processing. Okay, for a classical function, okay, this is some side note. For a classical function, if you give an input, right? This input, for example, 1, this input can lead to transform, or from after this function can give you a number, something like 2 plus phi I. Okay. But another number, maybe for example 1 plus I, could also give you that result, right? Another number, 7, can also give you that result. Is it possible to have many different input that map to the same output? Of course, yes. If you have a constant function, right? If you have a constant function, every input that you have will map to the same output, right? So this is not one-to-one. For classical information processing, it is transformation, it is not one-to-one. You cannot trace back. Given the output, you cannot know. In general, you cannot know what your input is. Okay, it is not, or in some sense, it is irreversible, right? But quantum information processing is different. If you know a certain output, for example, this, yeah, you can transform it, you can reverse the operation and find this. Okay, so this is one operation. So one operation give this, the other operation give this. So you simply reverse this G operation and you get back to 0. Okay. And for this reason, a general, this is also a side note. For this reason, a general classical gate require only one. So a general classical function or gate, classical, require only one input, and you'll get a specific output, and it's irreversible, right? And since quantum mechanics is reversible, you require 2 input. Okay. You require two input, and this is a quantum, and your output will be the function information will be contained in your in the second bit. Looks like this. In other words, okay, so this is what a general quantum function look like, and this is what a general classical function look like. You see the fundamental difference? Here you only need to use one qubit, and you can do the function. You can define a function, but here you need 2. Okay. All right. So this is just something at the side. Now let's come back to our task. How do we make a general state? How do we make a general state? Well, in this case, the block sphere will be particularly helpful, right? If I just say, oh, how do we make a general state? And I say, oh, this is these are two complex numbers. So how do I go from like one real number coefficient to two arbitrary? Like, how do I do that? It's a very difficult problem. It's a very difficult mathematical problem to think about, right? However, if we use this polar coordinate representation and represent all the qubits stay on the block sphere, this becomes an easier problem to think about because now it becomes a geometrical problem. Yeah. So now if I use this will mean how do I go from this state? Okay, if I represent if I represent this as the z, right? 0 as the z, and I just have some arbitrary states on the block sphere. Now the question is, how do I go from here to here? Now it becomes an easier problem. Do you agree? Why is it easier? I don't see how it is easier. Okay, let me put it this way. Here you have 4 degrees of freedom, right? Yes? 2 numbers in each complex coefficient, right? 4 degree freedom. So how do you go from one specific real number to four real numbers? That's difficult mathematically. Here you have only 2 degree freedom, theta and phi. Isn't that easier or what? It's easier, less task to do, right? And remember how we achieved this reduction. Last time we talked about this, right? We use, like for example, this and the modulus of CG and C needs to, the sum of the modulus needs to be equal to 1. Okay, and what else? Oh, and we also use another thing, the relative phase, right? It is the relative phase that matters, not the absolute phase of the individual state. It is the relative phase, right? So using these two conditions, we can disregard two of these numbers, and then reduce the test the number you need to find down to 6, down to 2. Okay. So now, since we cast this into a geometric form, this now becomes a geometric problem. Now the problem is phrased this way: how do you rotate a vector that's aligned with the z-axis to a vector that has a phi, theta, and phi coordinate? So this is theta, and this is phi, right? How do you do that? You use rotation. It'll be easy if you can use rotation, if you know how to rotate. But it'll be easy if you can just rotate it down to phi theta, right? Down by angle theta, and then do phi rotation along the xy plane. If you can break, if somehow you can break your action into 2 steps, rotating by phi, rotating by theta, and rotating by phi, then you can have your arbitrary state, right? So now the question is, how do we achieve that? How achieve the rotation transformation? If we can do that, this will be a simple problem. But how do we do that? If you remember in our previous lecture, we talked about N and R, right? in NMR, we have an equation motion that looks like this. Do you remember? Mm-hmm. Yeah. And here you have the, I also told you that the quantum Schrodinger equation can be cast into a form called optical Bloch equation. And that has exactly the same form as this. So the quantum Bloch equation tells you how this Bloch's vectors move in response to an excitation, right? And okay, typically people write this. They kind of reverse this order. Okay, but just so you know, the equivalent B field is minus of the Q, and Q here is defined as that. Okay, good. We're good, huh? All right. So this is just a little reminder that we have learned this before, and it'll be easier if we just deal with the resonant case. If we just deal with the resonant case, then we will have our effective B field in the XY plane. Okay, and then and basically you can just use your right-hand row to rotate your qubit state, and that's what we want to use anyway. So for if you want to process your quantum bit for this whatever purpose you want, there's no reason to use off resonant frequency on purpose. There's no reason to do that, right? You want a specific result, you will try your best shot on that. So you definitely use your resonant frequency. You will not make the job harder. Okay. So typically we deal with resonant case. Okay, and this actually in a more general form looks like this. If your drive has an initial phase, this effective field can rotate on the XY plane. Okay. All right. So I just want to remind you that last time when we talked about NMR, we also talked about optical Bloch equation, and this concerns the rotation of the Bloch vectors on the Bloch sphere, right? So I suggest that we can take advantage of this and use that for our rotation transformation. Okay, and let's see how it works today. We will see how it works today. Okay. So suppose I have, oh, sorry. I want to add a tail to this because this phi is different from this phi. Okay, this is the initial phase. All right, let me just add phi 0 and remove the tilt. This is the initial phase of your drive. Let's see the effect of this, okay? Shall we? Let's try with phi 0 equal to 0. Okay. If phi 0 equals to 0, then the q vector is on the x axis. This is your q vector. Correct? All right. So now from this equation, you see how it works is that you have an effective B field on the opposite direction, right? So this is your effective B field on the opposite direction. And how the spin moved is according to this cross product. So that's this. So you have a force that way, right? And if you rotate it here, you have a force this way. So you go in a circle on a YZ plane, right? Sorry. Okay. You see how this rotation is opposite. The normal of this rotation is opposite to your B field, right? So that makes it very convenient. Then you basically, so that basically means this will rotate with the normal vector along Q. Yeah, like double negative give you positive, right? Okay, so the rotation along an effective B field is to have its normal vector using your right hand rule is to have your normal vector going against the effective B field. So that means your normal vector is this. This is your normal vector. Your rotation normal vector. Okay. Great. So right. So if I apply, so now with this, I know it will rotate on this plane. What I need to do is phi to give me to a specific angle, phi, right? Do you know how much rotation you will have as a function of time? So you know this will make you rotate this way, but do you know how much rotation you will have as a function of time? If I want to rotate to here, how much time do I need to use? Yes, from the initial. So if I want to rotate to this south pole, how much time do I need to use? How much time do I need to keep this drive on? Okay. Now you have all done this microwave manipulation of the NV qubit state. You know the time is a key, right? And don't forget, this is what is this? This is the Rabi frequency. Yeah, and that specifies the interaction, right? That is proportional to the interaction. But anyway, that's the Rabi frequency you measured. Okay. Although in this notation, it is the Rabi frequency in radian, not the Rabi frequency in hertz. Okay. I mean radian over s, angular speed. Okay. Anyway, so if I want to, the question is, if I want to get to this position, theta equal to pi, how much time do I need to use? What is my tau? Yeah, you need to try to engage your brain to this, otherwise you fall asleep. This is so boring and so confusing and so convoluted. If you don't engage your brain to this, you can easily get lost, and this 2 hour or 1 hour will be wasted. Again, just use your experience with the experiment. I have a Rabi frequency. Do you? I tell you, my Rabi frequency is, for example, 100 hertz. How much time I need to turn on my microwave pulse? How long should my microwave pulse be so that I can flip the spin from 0 to 1? So this is one state, by the way.
1 over the frequency.
Almost.
It's my best guess.
Divided by 2. It's 1 high pulse, right?
Right.
Because 1 period of frequency is pumping.
Oh, yeah.
And then 1 half.
Right. Yeah. Yeah, correct. So Rabi frequency is, so remember Rabi oscillation? Yeah? Okay. So say we start from here. This is the 1, right? 0, right? And this is 1. Yeah? What's Rabi frequency? Rabi frequency is this. The periodicity of Rabi oscillation, right? And this is 2 pi over gamma. Sorry. Omega. 2 pi over omega is my Rabi frequency. So here, that will be half of my Rabi frequency, right? So this will be half of my Rabi frequency. Okay, that's how much time I need to turn this on in order to flip it here, right? How much time I need to turn it on in order to flip it to this XY plane?
P divided by 4.
Thank you. Yeah, I know this is too easy for everyone to answer. I understand that. I wouldn't answer this question if I were you. But thank you very much, Marlene. Okay. So that's how much time you need to turn on your microwave to rotate this to here. Okay. Now, so if you have just an arbitrary number, so now you know that this much time will give you pi, and this number, and this time divided by 2 will give you pi over 2. If you just have a random number like pi over 8, what should be the time? What should be the corresponding time to get you to that number, this angle? This number divided by 8. Okay? Okay, so now we have a way to get to an arbitrary theta, right? Great. What about phi? What about this? So when after we drop the spin vector down to a specific angle, how do we make it deviate from? So this is still aligned with x, right? No, sorry. This is aligned. My bad. This is aligned with, so do this, right? This is aligned with y. How do we rotate it? Because what we want is phi here, right? So we need to rotate it by this much. Yeah. How do we rotate it along xy plane? In other words, now we go from here to here, right? So how do we rotate it? Like this. You get me? Detuning? Let's see. Do we really want to use detuning? Can we not use detuning? Can you think of a way without using detuning? I mean, that's the last thing I would do. Because once you detune everything, right? Everything is like not at its optimum performance. Detuning has its place, yes, I agree. But you don't use it until you have to use it, okay? Experimentally. Now we're talking about experiment. Okay, we are very practical people. We're talking about experiment. We want to achieve this aim. How can we do it with the tool that I give you here? We change the phi, yeah, but how? You mean the static magnetic field? Well, we don't have a static magnetic field here. Let me remind you, because we are dealing with a quantum spin, not a classical spin. Remember? Okay, so we don't have a static magnetic field.
Then what else do we have?
I mean, we have the initial phase. So this means the initial phase of the microwave drive, right? And this means the amplitude of the microwave drive, right? And you can control how long you have it on. Yeah.
So the microwave?
Yeah, like, but what about the microwave?
Do the frequency of microwave related to the angle?
Let's see. No, because the frequency of the microwave is resonant or non-off resonant, right? So now since we want to deal with resonant only, then that degree of freedom is gone. It's fixed.
And then what else do we have? I mean,
Can we change the angle of this guy to make it? I mean, can we change this to, like, for example, here? And make it rotate in a different way? All right, let me give you my thoughts, okay? What I would do this differently. I would just do this again. What I would do is I will first start with not this. I will first start with uh, something that is, so if this is phi that I want, I will start with something here. So Q, this is pi over 2 plus phi. I will start with this. Okay? And now my circle will be here, right? And then I'll control my pulse duration to be pi over phi times half to this. Then I will directly bring it down to here. That's how I would do it. Okay? Yeah. All right. So great. This is a good exercise. Now I want to teach you a more systematic way to do it using quantum gates. Okay, so that was just like us trying to figure out how to do things. People who study quantum algorithms, they have to deal with much more complex transformations, and they cannot just do this, try and error like we do here, right? They need to have a very systematic way to do every task, a standardized way. Yeah. Okay. So now it's time to introduce quantum gates, and it turns out any operation, all operations in the quantum circuit can be pieced together using these quantum Legos. So here in this Lego state, we have x pi over 5 Hadamard C naught. Okay. So there are so many different possible gates, so many different possible transformations. This is the smallest set of Lego you need to piece out, to build a very complex circuit. Any complex circuit, actually. That's why it's called not universal. Universal. That's why it's called universal. Okay. All right. So what is X? And this is just language. S gate. It's also called a NOT gate. Okay. S gate flip spins 0 to 1. Okay. So in terms of, so if we represent 0 by this and 1 by this, if we use this basis, S gate will be this. It flip spins. Okay? And its circuit notation is this. A box with wire. Wire implies qubits. The left means input. The right is output. So time goes from the left to the right. That's the convention. So this box is your gate box. And here for X gate, we just simply put an X here. Okay? Now we have also phi over 8 gate. So now after this little exercise, I hope you feel motivated to learn about quantum gates. Because now you can piece out this with this finite Lego set. Phi over 8 gate. This is to add. So let me just put a little note here, just so you can see the function of it. This is to flip spins. Okay. This is to give a phase to the steady state. And as you can imagine, this goes like this. Right? But you might wonder why this is pi over 4. It should be pi over 8, right? This unfortunate nomenclature is due to historical reasons. So it's very unintuitive, but it is what it is. People call it 5/2 8 gate, but it is really adding a pi/4 phase. Okay? And this is represented by a box with a T. Yeah? And the very, very famous Hadamard gate. Hadamard. This is a French name. Hadamard. This is not a Japanese name. I used to pronounce this as Hadama. Like try to sound like Japanese, but this is Hadamard. Okay, this is a French name. French. This is a French name. Jacques Hadamard, a French physicist. HK. Okay, HK is to give you superpositions. This is to give you a specific type of superposition. Okay? Superposition on the X. On the X-axis. Right? So if I have this, if I know it looks like this, its metric representation will be 1, 1. That's this. And 1 minus 1. That's this. Right? So just try to apply this to here. You see that's how. You kind of just construct the matrix according to the function you need. Okay? And that's a box with H. Okay? So far it's not very creative. It's basically just a box with a letter in it, right? Now, C0 gate. So these are all single qubit gate. Has a single qubit input and single qubit output. C0 gate is a 2 qubit gate. And the notation is a little more creative. C0 gate. Okay. This means, so I have 2 qubits. Okay, I can write it like this. C means control. Not means inverse, like this X gate. Okay, so control NOT gate. That means one of them is a control qubit and the other is the target qubit. The NOT gate is applied to the target qubit. Target. And this is control. Okay? The NOT gate is applied to the target qubit, but whether the NOT gate will be active or inactive depends on the state of the control. In other words, control is like a switch. You switch on the gate or you switch off the gate. Got it? Yeah. It's like we have light here, right? And my eyes see light. When my eyes is exposed to light, for example, if this light is like super bright, if this light is on, my eyes feel pain. If the light is off, of course I don't feel pain. Now, whether this light is on and off have an effect on my eye depends on the state of my hand. Okay? If my hand flip the switch on, it's on, then hurts. If my hand flip the switch off, then it's off. No pain, right? So this is kind of fun. This is like a two.
Basically an if statement.
Huh?
Right? So it's basically an if statement.
Right, exactly.
The first one's the condition, and the second one's the action.
Exactly. This is an if statement. Correct. Thank you. Okay. So for example, if this is 0, 1, what should be the outcome? I should use the other color. What should be the outcome? Switch is off. Doesn't hurt. No, yes. Thank God. Doesn't hurt. Remain the same, right? Now, if I do this, it hurts. Your eyes closed. It hurts, right? You go from open, your eyes open, to your eyes closed, right? And this is the position of your hand. You flip off or if you flip on. Okay? So, how about this? This remain the same, correct? How about this? You were sleeping, and now your hand flip the light on. Your eyes open. Okay? Okay, good. All right, I just hope this analogy helps a little bit. And basically, all this can be summarized to this. This means the 2 modulo sum. Okay? The 2 modulo sum. That means if it's 2, if the sum is 2, then it is 1. If the sum is 2, then it will become 0. If the sum is 1, then it remains 1. Okay? So this is the modulus. So this is the modulus of A, B over 2. Got it? So this can be represented by this notation. Okay? In matrix element, it is how many elements we have here? Can you guess? And we will have a quick break after this. 4 by 4. Correct. Because here we have a 4 by 1 vector. So for a 2-qubit state, we have a 4 by 1 vector. For 3-qubit state, we have a 6 by 1 vector. Right? Is it 6 by 1? No. It is 8 by 1. So this is 4 by 1, right? Yeah, but if we have 3, we don't have a 6 by 1. We have an 8 by 1. That's how this works. Do you know why? Morning? I have no idea. Okay, remember how this works? If I have a number here, 1, 2, and this number is 0, 1. what do I do if I do a tensor product? I multiply this entire vector to this coefficient, first coefficient, and put it there. So it's like I multiplied it in element by element, but I remain its vector form. You get it? So if this give me 4 by 1, right? So by the time I finish this first two tensor product, I'm gonna do this, right? I will have 4 elements and the C vector, for example, 1, 2, will be here, 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 here. So there will be 8 of them, right? Yeah. So basically, this just goes like 1 to the power of 2, 1 to the power of 3, 2 to the power of 3. Okay, so that's how it goes. All right. So this is 4 by 4, but a 3 qubit gate will be 8 by 8. Okay. Cool. Okay. This is how it's written. Okay, so it's basically 2 blocks. You see, the first block is like an identity gate. Identity gate, I gate, is doing nothing. Okay, and that's kind of trivial, so I don't write it, but it's used everywhere. So the identity gate is this. It's doing nothing. Okay, so this is doing nothing. This is doing the reverse, the not, right? So whether the first one is 0 or 1 will determine this, whether it is the second, whether it is this one applied to this target qubit or this one applied to the target qubit. Yeah, so you kind of read it in blocks. That's the key of reading this big matrix. You're reading it in blocks. Okay, and this is all 0. And the representation is 2 rails. Remember, one line represents 1 qubit, right? So I have 2 qubit. That means I have 2 lines, 2 input. Okay, and the gate looks like this: dot and this. The dot denote the control gate, and this is basically the NOT. Yep. So what comes out is A. Yep. All right, let's take a 5-minute break, and then we'll come back.
天上演习课吗？你就可以写功课的时候一边放那个 physics，
看我这张纸这个大纲，
这种是可以放很多书。你办 physics 可以输入目电脑，但一个我，
因为有要换这个，
没有，它就是很多课本很简单。physics is easy 啊，现在有 AI 啊，那个它是从网页
有点晚学的。就是已经好久没有接到作业，好久没有要交作业。这只要买一张，那你买另外有机会吗？
讲就好了，我就没有说，就不卖肉，反正是买二手的。你有现在已经超重了。我觉得差不多，我觉得这差不多都符合了。这个是塑胶，这用这个是金属的，这塑胶很轻啊，就说这个很轻，哪有啊？它的电里面不算很轻，你要找到这个轻。对啊，这个是自身。
Yo, what is the website you talked about? Physics beautiful. Physics is beautiful. I need to look into this. Maybe it'd be useful to me. Oh.
哇，那超久，真的假的？
但是他都还没有什么问题。
我有点高三到现在
还有也是从书包里飞出来，
飞出来，
用跑步然后我们
它没凹进去啊，
没有
就少了一点气了。那其实蛮厉害的。但是 Mac 比较好用，Mac 超赞。我用到 Windows 之后就，受不了。对，我用了 Windows 3年了，我还是受不了它。宁愿用 Linux。
我真的没有。
太棒了，可以把自己做一下。对，可以直接把所有的字，你东西搞好，就按照它来。所以它的那个密也可以这种现场，就是你可以当做转接插吵架，然后你可以自己。
Okay.
然后这里面还有 Pad。
All right. Let's resume the lecture. All right. So now we have given a brief introduction of all these gates. Presumably, you have all the tools you need to construct anything, a general circuit, right? I do want to add one thing. So this phase gate, this pi over 8 gate is just very specific phase gate. The general phase gate is this. Okay, that's a general phase gate. Okay. All right, let's now come back to our task of starting with the ground state, and we want to get to an arbitrary state. Okay, and in this case, let me just use theta for now. Okay, we know in block representation is supposed to be theta over 2. Okay, so let's just give it name theta prime, because this makes the math easier. Theta prime. Okay, so how do we do that? With the quantum circuit. So if we are allowed to use this tool, only this tool set, and let me just add phase gate to it. If we are allowed to use this tool set and this little extension, what should we do? Turns out this is the circuit you need. So first with the H Hadamard gate, and then a phase gate. Oh, by the way, phase gate is represented by dot. Just dot. Okay, and then a phase gate of 2 theta, and then this 2 theta prime actually, and then another phase gate of pi over 2 plus phi, and then this. Okay, so let's see if this will work. This is the recipe given by people who studied this. Okay, let's see if this recipe works. The outcome, so supposedly you'll get ooh. Supposedly you will get this state. Okay, so in circuit notation, we go from left to right, right? In mathematical, in matrix notation, we go from right to left. So you first apply a Hadamard gate, yeah? And then you apply a phase gate of 2 pi, so phase gate. So everything is U, and then just put their specific name to the subscript, okay? And if there is like a variable, you put it like here. And then a Hadamard gate. Hadamard gate does not have any variable. And then a phase gate of pi over 2 plus phi. And then done. Let's That's everything. Okay? Let's write out all this matrix elements. So this is 0, 1, 1, E. Yes? And Hadamard is 1 over square root of 2 and 1, 1, 1 minus 1. Okay. This and square root 1, 1, 1 minus 1. I always go like this because this is one set. This is the second set. Okay? And I go 0, 1. That's how the matrix formula is written. And you can, for matrix multiplication, you can start with any of them, but you cannot exchange their positions. Okay? So what I want to do now is I want to just keep this for now. I want to keep this here. I want to keep this here for now. I want to see what this looks like. Yeah. Of course, I can just do one by one, but it's not instructive. I just want to see what this looks like. So, but this is basically, this pi over 2 is I, right? So this is I exponential I phi. So looks like this. Okay, so I'm going to do a little change here. 2, the square root of 2, 2 of them, that's 1/2. Okay. Now, so I'm going to multiply these two together. That is 0 exponential 2 0 minus here. Okay. And then I keep this. And then I continue. Go there. Minus. Oh, wait. Oh, I'm sorry. I have a typo. This should be 1. My bad. This is stupid. The face scared. This should be 1. So I had a typo. This place should be 1. And that should give you 1 plus minus 1 plus. Sorry. My bad. 1. Okay. Is this right? Yes, this is right. Okay. And multiplication again and again and again and again. All right. Okay. Who is really good with trigonometry. That means the conversion of, you know, this to one, like stuff like this, and sine would be 2 cosine. Right? If you're very good at this, then you can do this in your mind. Okay, you break this into cosine theta, cosine 2, cosine 2. So this is cosine 2 theta prime plus I sine 2 theta prime, right? And then you group the real part together, and then you do this, conversions, blah, 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 and then magic. Then you have the magic, and the magic look like this. And of course, you include the 2. Okay? So the magic look like this. Minus I, minus I. Okay? All right. The reason I want to do this is the following. Well, maybe I'll talk about this later. But what I'm doing is I'm trying to find operators correspond to this combination. Yeah, and that's this. Okay, so I want you to remember that. I'm doing this for a reason. Okay, so let's just circle it so we can easily find it later. Okay, prime everywhere. Great, right? Now it's, and sorry, forgot about the 1 here. 1, 1, 1. Yeah. So I forgot to put 1 here. There's a 1. Okay, that was a mistake. All right. So with this gate, now I can first transform using this gate to transform my 1, and that will be this. Okay, so it'll be this. And then plus a phase gate will be, when this times a phase gate, it will be Did I miss a minus? Oh. I don't know. I miss a minus. I don't know. Feels like I screw up a minus sign. Let me just, okay, never mind. So this, right? Okay, and so what should I do here is I need to make in order. So I have a little trouble here because you can see that my face here, I have an extra thing here I need to cancel out, right? So in order to get to this, so far I've got everything right, and this is, oh, you know what? No, this is fine because this factor is here. It's on both state, so it can be factored out. That's a global phase. Okay, we're good. And if it's a global phase, it doesn't matter. You can throw it away. Yep. One. Okay. So this global phase doesn't matter. This is equivalent to this state. Okay. All right. You might think this is boring, but it is actually a very important exercise to carry out all the multiplication so that you know how this works. Because any quantum information book that you read, they are so condensed, and everything's written in notation like this. And after you read like a page or two, you get lost completely. Okay, so just make sure if you have not, if you are dealing with a circuit, make sure you just spend 20 minutes work out the matrix to show it to yourself that this is correct. Otherwise, you get so lost. But now we see that this, if we don't carry this out, we don't know there is a global phase, right? So this is mathematically not equivalent to that. However, physically it is, because the global phase doesn't matter to us. Okay? All right. So now I want to finish this up. So we have gone through single qubit gate, and then we are using a single qubit gate to form a little simple quantum circuit, and this can bring any ground state to bring a ground state to this state, right? If you start with an arbitrary state, then the task will be probably harder. I don't know how to do that. But if you can do it for 0, you can probably do it for 1, right? And then you can just combine them, and it probably will be hard because there's always an easier way. Like the way I did it earlier, then I just used like one operation, right? But I have to use a very specific operation that is customized to my M, right? Here you just use a very generic set of quantum gate Lego, and this can achieve your purpose. Although it's kind of tedious, but this can achieve your purpose. This is fine for the computers. The computers do not care about tediousness. Okay, so this is sufficient for the computer. Let me come back to the physical realization of this. So earlier we were talking about like how do we do this physically to how can we physically transform this to that, right? And then we talk about rotation transformation according to our excitations and that, right? So I want to come back to that. I want to talk about how do we do, how, like, this is all very nice and great to define mathematical matrix in transformation, but the question is, how do you realize it? Yes? So first, how do we realize Hadamard gate? When you think about physical implementation, you want to think about the block sphere. Okay, and you want to see how this rotates stuff. So this rotation is from, so x, y, z, right? This rotation is from, the Hadamard rotation is from here, 0 to this. And the second one is from 1 to this. Yeah? This is the Hadamard. What would be the corresponding operation? Microwave operation for this. Let me just give you, so remember we were using Q, right? And Q is, in the general form, can be written as this. Right? Okay. Let's try to define a gate transformation for it, okay? What this does is it rotates along an axis that is pointing towards cosine phi 0 and sine phi 0 and 0, right? So if so this define the axis. This is the unit vector defining the axis. Yep. So let's say the rotation that according to this is along this axis. Okay, along this certain axis, and then how much you rotate depends on how much you turn this on, right? So that's this. Yep. Okay, so our okay. Pi over 2. Yeah, let's just stay with that. And this theta is, okay. So so now we have already defined the microwave operation as this rotation thing. Hadamard gate is basically a rotation along the y-axis. So we could write it as r, y, yeah, and it's rotating to half plane, right? So that's right. Okay. Yeah.
I'm sorry, but I don't remember how you represent the states on the H gate on the as vectors on the block Like why is
Why is it rotation?
Huh?
Why is it rotation?
Why is Kent 0 just set up?
Oh, that's how I define my Bloch sphere.
Okay.
So I can define my Bloch sphere with the north pole aligned with 0. That's just by definition, by construction. So according to this definition, then remember this, the general expression that we have. So if I define this as 0, no, sorry, z. If I define this as z, then theta will be the angle with respect to the z-axis, right? So theta, if theta equal to pi over 2, then I am, so here. So if theta equal to pi, then this is 0 and this is 1, right? Then the minus z will be my south pole. Okay. So this is minus z. Okay, and x will correspond to pi. So x will correspond to pi equal to 0 and pi equal to half. Yeah, I don't know if I probably didn't say this. I'm sorry. You're probably right. I probably didn't say this. Yeah. Anyway, so last time we talked about Bloch spheres and let's just have everything defined in terms of the vectors. Okay. So for the Bloch sphere z will correspond to, if the Bloch sphere z is corresponding to 0, then the x will correspond to 0 plus 1. Yeah, and y will be just this with a pi over 2 face, right? A 90-degree face. So that's this. I. Yeah. And minus x will be phi equal to pi. Yeah. So minus x. Let me just write it with small, very small. Yeah. And yeah, that's probably what confused Marlin, because I didn't spell this out. And minus y is 3 pi over 2. 3 pi over 2 will be minus I. Minus I. Okay? All right, so I hope this is clear now, that x minus x, y minus y, they correspond to this state. And that, because they have specific coordinates, right? So once you fix one of them, the relative relationship is the same. So you have this 1, 2, 3, 4, 5, 6 state. Their relative orientation are the same. So if you fix one of them to z, the rest will just fall into place. Okay? So in this convention, if z is the null pole, if 0 is the null pole of Bloch sphere, then x will be this, and minus x will be this. And that's what the Hadamard gate give you. You rotate your Bloch vector from z to plus x, and from south pole, minus z to minus x. Got it? All right. And this corresponds to a rotation operation, transformation that is denoted like this. Yeah? And okay. And this is, of course, like I said, this is the pi over 2. That is our pulse, right? Okay, so that's Hadamard gate. How about phase gate? How do we accumulate phase in the excited state? Next, next, never mind. Okay, how do we do this? Remember, if you just let the colon system evolve, what will happen? Just you prepare it to a superposition state, okay, and you just wait. What will happen? Because great, you guys are very smart, but I'm talking about just like ideally. Right. Yes. So a phase, a natural phase, will be added to to the excited state, right? And actually, this is minus, right? So the sign is important. So if this is your 1, this is your 0, and this is your omega, that will accumulate state at the rate of minus omega t. Okay? So and of course, if you want to, so you want to accumulate a specific phase, for example, 3 pi, or let me just write like this, right? What you should do is that you should, that is evolve. And of course, it's kind of silly here because you have a minus on the right hand side, but you have a positive on the left hand side. What do we do about that? The easiest way is just to transform this into the minus, because we know phase are the same for an integer number of 2 pi, right? So this is 2 and 2.5. So this is 2.5 pi. So what I would do is I will just minus this by 2 pi times 2, right? An integer number. I will first transform this to a negative value, 2 pi over 2, so that's 4. So this is minus 1.5 pi. Yeah? So having transformed this to a negative value, I now can calculate how much time I need to wait for this to evolve. Got it? Yeah. I can calculate this is the amount of time I need to wait for the system to accumulate 5 pi over 2 phase. Okay, so wait, by simply waiting, is a gate operation. Okay. There is, let me see. There's a specific there's a specific phase gate. It's called, oh no, never mind. Okay, yeah. yes, do mind. So there is a specific. So if this is pi, if phi is pi, a pi phase gate will be this. A pi phase gate will be this, right? And just let me remind you, this is also called the Z gate because this corresponds to the Pauli Z matrix. And this is called X gate because this corresponds to the Pauli X matrix. Yeah? So if I want to do a Z gate, and this is actually is called Z gate. So a specific phase gate like this is called the Z gate. Okay, because it's useful. You flip the sign of the excited state. You use that a lot of times. How do we achieve this? Do we just wait? Or is there a better way to do this? Okay. So it turns out that if you apply a microwave pulse and you do 2 pi, yeah, if you do 2 pi, the population will stay the same, right? However, the phase will change from positive to negative. Okay, a lot of people didn't know that. A lot of people just think, okay, if I just do 2 pi, everything will back to normal. No, it is only the z component, the w. So UVW, the w will return to its initial value, but the u and the v will not. They will go to the other side. Okay, so there will be a pi phase accumulation. So you need to make actually 2 Rabi cycles in order to return to your very original state. Okay, so therefore we can use that. We can take advantage of that. Just apply a 2 pi. So this is basically a 2 pi Rabi rotation. Okay. All right. So that's this. X gate. X gate is flipping this to here, right? Mark, do you know what this corresponds to? What rotation operation this corresponds to? Let me just draw with orange. So this is the X gate. Come on, you can insert this. You don't need to ask Han. What's the rotation transformation I need to apply to make the flip? Speak loud. Can I ask again? Okay, I'm going to ask you the third time. What rotation operation do I need to apply to flip the spin from 0 to 1? That's the X gate transformation. That's the X gate operation. I give you 3 counts. 3, 2, 1. Can you answer or not? Yes or no? Don't ask you. Come on. If I want to answer from him, I will ask him. Do you know or not? Yeah, that's what X gate do. But I want to know what physical operation I need to perform to realize X gate. You don't know? Just say you don't know. If you don't know, say you don't know. Okay, that's fine. Next person. Who is taking notes? Okay, I probably will have a better chance with people taking note. Oh, you're taking note. Are you taking note? Are you taking note? Are you sure? Obviously, you're taking note, Finn. Okay, so probably you can help us. What is the rotation transformation we need to do here to realize X gate? Oh, that's great. That's a good start. Pi poles. Yes. And how do we represent pi poles in rotation operation? In rotation notation. This is the rotation operation notation. Okay. Yes. Yes. How do I write this? R, right? That's a good start. And then what? What do I put here? Yes. And 1 is here. Yeah. 1 is here. Yes. Pi where? Like in the bracket? Pi? Like this? Okay. What do I put in the subscript? Z? Y. Okay. Great. Thank you. So Hadamard gate is rotated along y by pi over 2. And the X gate is pi. So these are just the pi poles and the pi over 2 poles that you use. Yeah, isn't that simple? You already covered 2 of them in your experiment. And this is you do just by waiting. Done. You already know how to do 3. And since we only have a single qubit machine, we cannot do C naught, yes? Oh, right. You're right. You are right. And why is that? I wonder. Okay. He's right. He's talking about there is a phase, right? Is it if we rotate by this? Oh, I see. I see. Right. Oh, is it? Here? Oh, so rotation by y will give you this? Oh, I see, I see. Okay, thank you. All right. Thank you, and that's a great point. Thanks. Right. All right, so you see, physically, so this state, this state and this state are physically the same, right? Agree? Because they only differ by a global phase of -1 or a global phase of pi. Correct? Yeah? So these are physically the same. So you can use rotation transformation to reach this. Yep. because this axis, this block notation does not distinguish the difference between, does not distinguish the global phase. Okay, so this is not wrong to just write this there, right? However, the Hadamard gate have a very specific requirement that the minus sign needs to be on the excited state. Yes. So we need to be cautious. We need to be careful with that. And it turns out that this rotation, mathematically, physically, give a state that is equivalent to the supposed your target state. Physically, it does that, but mathematically, it actually gives you this. And how do I know that? Because I can write down. And that will take another half 30 minutes, so I probably don't want to do that. I can write down the Rabi solution. Yeah, so I'll give you an outline. So CGCE. So this is, remember last time we said this is a function of something with CG0, something with CE0, CG0, and CE0, remember? Okay, I wrote this on the board in the past few lectures. This is a Rabi solution, right? Okay, and you can turn this into a matrix CG0, CE0. Yeah? Okay, and this will be just the unitary transformation on the initial wave vector, on the initial block vector, right? Yeah. Right. Turns out this transformation has exactly this rotation matrix form. Okay. So I was showing you how this can be done qualitatively, but you can derive it rigorously using the Rabi solution. Okay, and then you can derive the exact form of the R transformation. And it turns out that if you do this, according to that exact form, if you do this, you'll get this state. It corresponds to this. Okay. So in the menu they call this quasi-Hadamard gate. Okay. Although nobody used that term. So I was a little wrong, not totally wrong, but a little wrong. So in order to of 100% reproduce the Hadamard gate, you need to follow this by X rotation, and yeah, but that doesn't rotate it, right? That's like a phase gate, right? Yeah. So anyway, you need to follow it by an X rotation of pi. Okay. So since this state is in this axis, it's along X, applying an X will not change its population, right? Because this is in the same axis, right? However, it will change its phase. When you don't excite it, so what happened is when the pulse comes. So physically, what happened is when the pulse comes, the population will change with the pulse. However, after the pulse is gone, the population will come back. Yeah. So this is what it means by not changing its theta. Okay. But the pulse still have an effect on the population, just by going like this up and down. It will leave some effect there. This is similar to this z gate thing that I told you about. Okay. So anyway, so this two combination, this followed by that is the Hadamard gate. All right. All right, so enough with the single qubit gate. Oh, okay. Coming back to this. So remember, I specifically marked this. H followed by a phase gate, followed by H, right? Now you know H is a pi over 2 pulse. I wonder if you can recognize this sequence. This is the Rabi. This is the Ramsey. The Ramsey pulse, right? You first apply a pi over 2, and you wait, right? You wait. That is the phase gate. And then you apply another pi over 2. Okay, so this is very, I'm not saying it's exactly the same. Of course, because remember we have this additional vector. So it's not exactly the same, but this is very similar to our Ramsey. Yeah? Our Ramsey will be Ry pi over 2, and then the phase gate of however long, and then Ry pi over 2. Okay? All right. Now, finally, discrete quantum tomography, and this will be very, very fast once you get a hand of this rotation business. And then we are done. And then next time we'll talk about quantum algorithm, the Deutsch algorithm. And then we will be very much done. And everybody will be happy. Okay, lastly, quantum tomography. What is tomography? Tomography means you get a full, it's like a dissect of, it's like a full analysis, okay? Right, yeah. Tomography in medical application means you have image that is the slice of your bodies. And when you put them together, you can see the full thing, okay? Here we're not doing that. But here in physics, tomography basically means obtain the full information. Obtain the full information. So what is the full information? For a quantum state, the full information is in the density matrix, right? Decohere or not, the full information is here. Remember? So four elements, and each of them are complex numbers. And then last time we talked about this and how this can be reduced to 3 numbers. And these 3 numbers correspond to the block vector. Yes? So if you know U, V, W, which is the block vector, you know this guy, right? Okay, so if we know the density matrix, we know everything. Even if it's decohered, we can estimate how much coherence is left, right? So this gives us the full information. So tomography basically means to obtain the complete density matrix. How do we do that? This is actually not a very difficult task. It sounds easier than it is easier than it sounds. Okay, x, y, z. So suppose you have a vector that has a component only in the x. Okay, and you call this u. Okay, so let me just call it vector number 1, u. How do I, experimentally, how do I know this number, including its positive and including its sign, positive and negative? Okay, what do you suggest, Xi? Pi over 2 poles, gray. Along which direction? Like this? You want to go to here or here? Up? Okay. Want to go up? Right? We go up, then that's a very good suggestion, because if we can somehow make it go up, right, then we can detect the population difference. Remember? Our measurement is to detect the population difference. In other words, whatever is on the z-axis, that's what we detect, right? Our signal is proportional to this. Yeah. So if we can just somehow make this flipped there while keeping the sign and magnitude, then we know what this vector is, right? So how do we achieve that? A y rotation by this 3 pi over 2. 3 pi over 2. Right? 3 pi over 2, of course, is the same as minus half. Right? But we try to keep with the, so this gives us the right-hand row gives us the positive angle. So if you want to do minus 2, you need to transform that to a positive angle. Okay, so that's this. Okay, so 3 pi over 2. That's how we do it. Next, if I have the second block vector, and that has only a component in the v, in the y, how do I measure it? Do I use a y gate? Do I use a y rotation? Huh? I use an x rotation, right? And in this case, it's pretty simple. It is just pi over 2, right? Okay, great. Third. Okay. If I have a vector that has a w component, z component only, how do I measure it? You don't do anything. You don't have to do anything. Just directly measure it because it's already on z. Yeah, because whatever you measure is the information on z. Okay. What you measure is the difference between this and this. This is PE. This is PG. G. The ODMR signal is PE minus PG. So that's this. Okay, so we are measuring, so when we measure, we are measuring minus omega, right? So you don't do anything. Basically just I, okay? So that's the tomography, pretty simple, right? So now when you apply a series of gates and you want to know what your quantum state look like, your quantum state might look like some kind of, it could have like some arbitrary numbers, right? How do you measure this? You do it 3 times. So that's the slices. You slice it according to, you slice it in one direction, you see U, you slice it in another direction, you see V, and you slice it in another direction, you see Y, W. Okay, so you do this, you get the U prime. You do this, you get V prime. You do this, you get W prime. So if I have so in the lab, you're asked to do a tomography of a Rabi process. Previously, okay, so let me just draw it like this. Previously, you only do this. This is the Rabi, right? And then you just measure. You go start from the ground state and you just measure. Yeah? And your measurement give you W or minus W. Yeah? Now, yeah, actually, I'm sorry. Actually, in our ODMR, we use PG minus PE because this has a higher fluorescence and PE has a lower fluorescence, right? So this gives us a W actually. So our ODMR give us the exact W. So no minus sign, so just the W. So this is our previous scheme, yeah? Now, I want you to, so and this give you this. Yeah, so this is W. And in the lab, I want you to do U and V. I want you to find the trajectory for U and V so that you can know the full trajectory of the blocks vectors on the spheres. And you can see how it goes with the poles. And it's kind of cool to see that. Okay? So what do you need to do there? So after the Rabi poles, whatever Rabi poles that you're using, you can use the pi poles. So that'll be an X gate, right? Or you can use the Hadamard poles, whatever. But if you want to do U, what do? You add another thing called Ry. Ry 3 pi over 2. And that gives you U. So two pulses. So and then if you want to do V, you add Rx pi over 2. That gives you V. Yeah? All right. So that's how you do it. And how, if you don't add anything, it is a y. If you don't change your face, right? If you so your pose is like this. If you don't change your face, so you start with 0. What does that give you? Actually, I think because in yeah, it's a little complication because in the Rabi solution, you assume a drive that has a cosine term. Okay, that is a cosine. So it looks like this. So this means you start with this. So this is the Rabi solution. Yeah, and this will correspond to Ry, I think. No, Rx. This will correspond to Rx. Okay, so in the lab, what we have here is Ry, yes. So this is Ry. So if you don't do anything, if you don't mess with its face, it's Ry. And if you add a 90-degree, okay, so X, Y, Z, and this is your 0. So if you don't do anything, your axis is here. This is your Q. Okay, and then if you do a pi over, if you add a pi over 2 to your initial phase, then you have a minus X. Yeah. So in order to have an X, you need to add 3 pi over 2 for the initial phase in order to have Rx. So this is just your microwave. This is your microwave with 3 pi over 2. So that's 270-degree phase offset. Yep. All right. All right. So that's quantum tomography. So it's not as hard as it sounds, but it's super interesting. If you can do quantum tomography, you can monitor the decoherence process, right? Because in omega, you have the decay, you have the relaxation rate, and you also have the decoherence rate because omega depends on U and V, right? And U and V, it will drop according to the decoherence rate, pure decoherence rate. But when this drop, this will drop too. So even in the absence of relaxation, even your relaxation is like super long, this will still drop, diminish. So when you measure omega, you have an effect of both relaxation, T1, and decoherence to T2. If you can do tomography and see the trajectory of U and V, you can isolate the decoherence signal and then just measure the pure decoherence time with the Rabi method. Isn't that cool? I think it's cool. All right, so cool. Thank you very much for your incredible patience. We are towards the end of our lecture series. The quiz today is quiz. One. Where's black? I don't have black. Okay, whatever. Yeah. This is even worse. Yeah, I think they are out. Oh, no. with number 1. All right, let me just put it in this way. Okay, so so we have 3 numbers. Okay, we have 3 numbers. If the coherence time is 600 and the Rabi period is 100. Oh man, this is hard. Yeah, this is a tricky question. If the coherence time is 600 and the Rabi period is 100, what is the maximum number of X gate we can apply?
I don't know where to start to think about this question.
Then you need to debate with them. You need to ask them.
Huh?
You need to ask your peers or debate with your peers. Okay, let's stand up. Now it's your turn. I've talked enough. Like, this is the time to.
Does anyone have any idea?
Thank you. That's the spirit.
My idea is 10, but it's not an option.
Why is it 10?
My idea is you have to set it up first, right? And then it's pi pulse to set it up. So that's 100 nanoseconds. And between 100 nanoseconds to 600, there's 500 nanoseconds of time. And X gates takes.
point you
Half
have
pi.
pi plus over 2 period over 2.
Pi pulse is, huh?
Because pi plus is pi n. To turn around is 2 pi. And
Right, yeah.
a whole period turn around.
Yeah. Oh, okay, my bad. Then it's a limit, but it's still not. Okay, okay. The explanation is x gate turns half, right? So it's also pi pulse, which is also 50 nanoseconds. And so if you 600 minus 50 divided by another, divided by 50, then it's 11. That's my explanation.
Good try.
So you say the answer is not there. So I'm gonna create a box for you, and you can fill your own answer. Hey, but there's only one box, so only one answer is allowed. You guys need to decide what answer to put there.
Can you draw your idea? So we have this set xy, and this is 2 pi.
So initially we need a initial pulse setting to 0, right? That's let's just set this to start, and then we need a caliber 2 to set it at 0, and then after that one x gate operation is another caliber 2. So it's
So how do you how do you know that this is like it depends on where you start from.
and it's starting time is 0, right? When you start doing the experiment.
And
And you
what
set
does that correspond to?
at start we doesn't know the population in the any center, right? We have to set it all to 0. That's what the purpose of the first excitation pulse is. So after the first excitation pulse, we know everything will be on.
This is horrible.
Okay, and that is not
So we have people lining up. Great.
from
4, 5, 6.
No, once we set it on 0, then it's on black.
Yeah, but I mean this.
Yeah, it's not. And then after that, it's just like.
We know the counting would say. Yeah. Okay, so that's how you get there.
Yeah.
Okay. Yeah.
And after that, x is caliber 2. Okay. So x is pi, then minus 600 by 50.
What's your gut? What's your answer? 6? Great. What's your answer, team? 6. How about you? 12. Okay, great. How about you? 6. How about you? 4. Great. So we have people lining up for 6. And the 12 over there, are you waiting for them to finish?
Okay. So it's 575 and divided by pi, which is 50. So that's 11. That's 11.5.
Eden and I, we don't have black. Could you grab 3 black? If the office is still open? Yeah, thank you. They are out of this? Okay, there's 1 black. It's only 1 black. This is a good one. So they are out of black? Why? Tell them that there's no black in this. There's only 1 black here. We need at least 3.
Why do you need 3 black pens?
because I'm walking in 3 positions. 1, 2, 3.
Okay, you can put it in your pocket.
How about I put it in your pocket and then you just follow me around? All right, line up. Thank you very much. Okay, so you guys are on a special box, and you are like nowhere, a no man land. What you need to, if you want to stand behind the box, you need to put a number there.
We have different answers.
So you need to decide one.
11.5. Now, how do you have 12?
Yeah, you can start from zero. As you start from zero, and you can starting at the x-ray. You just 16.
Like you don't set it to 0.
Yeah, we don't.
Oh, okay, fair.
It's just the
Okay,
QB
fair,
for
yeah. Okay, I'll agree with you. 12. Okay, Carol.
Yeah.
Okay, are we done? So they agree on 12. All right, so we have a 1, 4, 3, 6, 2, 12, and you, Madin?
Yeah, I don't have any.
You don't have any. Great. All right. Yeah, why don't you talk to this gentleman? Why you shouldn't have any, and you two will talk to them, and Ting will just play with the whiteboard on home. Okay, so you guys talk. Try to convince each other.
Okay.
Actually, I'm not sure. But my first answer is
English, please. Do.
there's no choice. So
Is that a snail?
maybe we can
Yeah.
do and 0 to 1. 1 and 5. Maybe we can do 600. I think what is typos. When I because the rock is like too tight and it will back to the result. Yeah. So it's okay. Rotate around x-axis 0 to 1 and 1 back to 0 is I guess maybe not here. So maybe that's just how it works. So and 100 cosine that's it. Okay. So 600 divided by 100. Yeah. Okay.
Are you done? Are you fully convinced? So you're cheering for number 6, right? Seems like you're cheering for number 6, Tin Snail. Could you, Tin? Would you mind after you finish decorating your snails? Would you mind talk to Clement and convince him to come to your team? She is very confident it's 6. You can tell by her drawing.
Inspired by Clement because he said that we have to first do the first tripod to align the MV center or the screen to our observation axis, and I feel like that kind of makes sense. So if we have to align it every time, then it will become so for one x gate. If this x gate is limited to some initial condition, then we have to reset that every time. Then one period for the x gate is 100 over 2 and multiple by 2, so that's 100, and then takes 600. And I would like to choose 12 if you put 12 on, but you didn't, so I'm trying to convince you with this one.
Wow. Thank you for a very convincing and complete argument.
You can set it up by using a Python.
Yeah.
How we do that?
I know, but I think I kind of saw that on the manual saying that if we apply the Pythons, we can try to align it. And that I don't know the process, but that's just a test.
All right, great. Thank you very much. I appreciate all your answers. All right, so do we have now a final vote? Are you coming? Are you joining the herd?
With your team.
Huh? You're with him? Okay, then please go to number 6, and you probably can decorate the snail together. And how about you?
Yeah, I joined the snail.
Wow, man. And then you guys, you're still rooting for your 12, right? And you?
6.
Oh gosh, man, you're popular. All right. Congratulations, Team 12. Yeah, but I appreciate your argument. The initialization, however, is not done by the microwave. It's done by the laser pulse. The initialization is done by the laser pulse.
How? So this was just a trick question.
Sorry, how? You shine green light to it, and through optical pumping, it initialized to 0, right? And so that's one thing. However, this is theoretically true, but not practically true, because in each pulse you do need have a little gap, right? I mean, a minimum gap of 10 would be nice. Okay, so I would say maybe 11 pulse would be okay. So if this is 50, so that 50 is for pi flip. X gate. So we don't need to reinitialize it. So like here, what I mean is, I want to apply a series of X gate. So I keep flipping it. Like this. And of course, you need to have a little wait time in between. Otherwise, your pulse overlapped, right? So I mean, for our experiment, this is the minimum is 10 nanoseconds. So you want to estimate a 10 nanosecond for each X gate. So that will be 60. Okay. So I guess that will mean for 600 that will be 10 gates. 10 gates. But thank you very much for the lovely decoration. That adds the spirit to the class. Okay, so 10. 10 I would say is, yeah. Yes, a trick question to just get everybody thinking. Second one, can we apply 3 tomography pulse and obtain the density matrix in one single shot? So just like block, and then you're done. You don't. You know, I'm gonna keep that snail for the next class. Okay. So yes or no? Can we apply 3 tomography pulses and obtain density matrix in a single shot? So that means, can we do this? 1. So this is your gate, okay? Whatever gate you have, and then you have the 3 tomography pulse, and after that you get WV and UVW. You get all information in like one series. Can you do that? Everybody vote for no? Yes? Are you voting for no? No? Oh, no? All right. Great. That's correct. So tomography means you have to do it. You have to do each slice individually. So only one information at a time. Okay? So So you cannot just do everything in one shot. You need to do at least 3 times. All right, thank you very much. So that will be it. And let's move to the lab and use whatever time we have left to work. Yeah.
How do we know the microwave we apply is right is which
RX, RY.
Yeah.
So without the thermography, you cannot. Okay. But like I said, so so if we assume cosine, the cosine drive in our Hamiltonian, then this will give us without zero with zero phase. Okay, this will give us effective field like this. This is the delta. Okay, so in resonance, if in resonance, then this will be, if on resonance, this will be 0, right? So this will
no initial phase.
no initial phase.
Initial phase
No, this is just theoretical. So if we do theoretically, if we derive this theoretically, then this will give us Rx. So this is Rx, right? Now, what does this correspond to? This corresponds to this. Right? We start with the maximum value. Yeah? But in our lab, we didn't start with the maximum value. We start with this. We start with 0. So we do this. Right? Therefore, what we have is sine. Yeah? So sine is so sine means this is I'm always confused with this. Not pi over 2, right? Minus pi over 2? Is this minus pi over 2? So plus this plus, yeah, minus pi over 2.